Should I start now?
Yeah, please.
Yeah. Okay. Yeah. I just checked why the symmetric linear quantization are used. So compared to the symmetric linear quantization, so it's possible to with the more integers. But the advantage is it's very simple to implement. And on another side, for the weight itself, it always have some distribution like the normal distribution. So in practical, so it's possible to have the R min and R max which have the similar absolute value. So for the symmetric linear quantization, it is also possible to use a lot in the real world.
Okay, well, how is it simplified as compared with
Because the z is equal to 0, the 0 point would be 0 in the
metric
thing. Yeah.
and you just multiply s with q.
Yes.
Okay. Yeah, Sui has an exam at 1:20. I guess maybe Sui, you can present first.
Okay.
And then Xin can supplement her remaining.
No problem.
Yeah, please share your slides.
It's my first time to use the iPad to join the meeting and finding how to share my screen.
I think it's still on the Zoom app, right?
Sure. Yeah. Do you guys see my screen now?
Yeah.
Okay.
Yeah, we can see. Okay, fraction Fourier transform. Okay.
Okay. So today I'm going to introduce a transform kind of like the advanced version from the Fourier transform. So I'm going to talk about what's the difference between the fractional Fourier transform and the Fourier transform, and what's the benefit that it can has the what the benefit they can have from the Fourier transform and from the multi-wavelet transform. So yeah, and afterwards I will talk about how it works and how to implement it and what did people do during the period. Yeah. So first, talk about the regular one. So in the Fourier neural operator, they just imposed the operator into the convolution form, which means they just put the kernel functions into this form so that they can use the convolution to compute the integral over there. And so by this way, they can use the Fourier transform to filter out the noise they don't want. For example, the example on the right, so we have the three signal, and if we just take a look from time domain, we are hard to tell which one. I mean, we are hard to tell between them. So by transform them to the Fourier domain, we can easily to know them. I mean, case by case. So in the Fourier transform, in FNO, they decide to use a a kind of like a filter to filter out the high frequency, which means in this case, they will get rid of the data in high frequency and just keep the lower frequency data and transform back to the time domain by this way to get the real data they want without any noise. So this is what FMO did, and in a wavelet neural operator, their goal is to solve this integral as well, but they use a different transform to do that. They just divide the integral into two parts. So the data part, and the operator part. So the data part, they can use a wavelet to divide the data into two parts, the time part and the frequency part. And the operator over there, they can use the formula from textbook. And by this way, in time frequency, in the time and frequency domain, they sort of like they can divide the data. So like here's our data, here's our noise. They kind of like divide the frequency and the time by this way, and divide again, so that they can get two parts, the time part and the frequency part each time. So by this way, they can just divide until they run out of the data, and they will use the formula here to multiply with the part. These two parts we divide, they multiply them together to get the answer over here. Yeah. So from their result, they found the performance is better than Fourier transform. However, there is a disadvantage from it. It's pretty slow because with high, I mean with as many data you have to divide them as many times. So it costs a lot of time. Yeah, but from these two methods, we can note, the Fourier transform, what's the benefit from it? It's simple, but the lack of the time information, and the wavelet is complicated, but they can get the time information at the same moment they get the frequency information. I mean, they have a frequency and time, and like this guy, they only have frequency. So that's the reason why I start reading the fractional Fourier transform.
So
In
yeah,
FM,
I guess to be more clear, you're saying like when you're doing filtering, in Fourier transform, only consider the frequency, the amplitudes for those frequencies, and the multi-level wavelets can consider both the frequency and time information.
Yep.
Okay.
Yeah. And yeah, in this page, I just want to explain in high level what do they do. So so here like here is our data. We can see it by the time, and here is the amplitude. So if we use the Fourier transform, we just like we stand in here, so we can see a lot of frequency. We can see a lot of frequency in this square. And if we use the wavelet transform, we kind of like stand here to watch the wall, and we can just see the frequency information and the time information up here. And the fractional Fourier transform is kind of like they are watching the wall as well, but not as complicated as multi-wavelet transform. The FRFT is kind of like they just draw a line in this space so that they can just project the data and signal on the line, and we can just easily to tell the difference between the signal and the noise. That's it. So here is an example about the definition and how do we how do people implement it. In this paper, the black part is a noise, and here is a signal, and here is the fractional FRFT. They can just draw a line in this space, and we can see three signal on this line, and we can easily to tell the difference from it. And here is their define, and it's just like the wavelet, like a Fourier transfer. They have the signal and have a kernel function, and the kernel function is over here. Is pretty complicated. However, in 1996, I think there's a guy they presented a approximation, a way to calculate the integral over there. So how does the approximation work? So here's the data we want to transform from the time to the specific domain they called alpha domain, from time to alpha domain. So how do they do that? The first, they just multiply with a function they called chirp function. The chirp function means there's a function and the frequency, like there's a chirp function, which means the frequency goes up by time, which is chirp function, just like the one over here, So by the time, the frequency just goes up, and the chirp, it can be found on Wikipedia. So after multiply with the chirp function, we will do a convolution with chirp function again. And after we get the G pound, we multiply it with chirp function again. Then we can get the data, but on alpha domain. So basically is
sorry, where does A or alpha take effect? Is inside the chirp function?
No. The alpha is independent from the. It's over here. Basically, alpha phi is a constant.
But A phi, as in equation 1, it only contains phi, right?
Yep.
Where is alpha? Or alpha is phi? Or phi equals
phi. Yeah.
Oh, okay.
Equal to how much 90 degrees you have. Yeah.
So A is a continuous number. Okay.
Yep.
So it's the sign of sine pi.
Just the sign, the positive, negative.
Okay. But what if A equals to 0? If A equals to 0, then the denominator becomes 0, right?
Yeah. They have a special case in here in the kernel function. If the A is the multiple of the 2 pi, they have the impulse function over there. Dirichlet function. I forgot the name, but they have an impulse function over there for some special case.
Okay, so how they gonna compute? So fx, what is fx? Fx the original signal?
Yeah, the observed signal.
Observed signal in the time domain, right? In equation 16.
Yep.
Then you construct G by multiplying it with the so-called chirp function.
Yep.
And then you just do the integration. It's kind of similar to like Fourier transform, right? In 15.
Yeah, it's just a convolution. So we have to do FFT to each. I have to do FFT to each, and just multiply them and transit it back.
Okay, then you multiply the G prime x. G prime is actually the transform signal. Then you multiply with the chirp function again, you get your alpha transform, right? You get a signal on the alpha domain. Equation 14.
Yeah. We multiply again, we can get the one over here. So by different alpha, we can just put different lines on this space and just to see which line is the best to tell the signal and the noise.
And here
So,
is x a complex number or a real number? Or it's fine, it's just like a Fourier transform. Like your input can be generally complex numbers.
So Fi is just a real number. You can be 0.1. You can be any number. You can be 100, but it will only just get between the 0 to 2 pi between them. I mean, it's just like a circle. So when alpha equal to 1, the approximation over there, the definition over there, just equal to the Fourier transfer. That's it when alpha equal to 1. So Fourier transfer is one of the...
Alpha, I guess what you said is phi here, right? When A is 1, phi in
the alpha, I mean, is the A over here.
But you said A is between -1 and 1.
At 0.1 to it can be any number. Yeah, it can be -1. I mean, it just like this one here is the time domain, is a frequency domain. Yeah. Yeah, and the here is the phi, and the phi is equal to how much alpha we got. That's it. So it can just get round.
Oh, okay.
Just depends on how much you want. So alpha can be any number. You can be minus. If you be minus, the angle just start from here.
Yeah, but you write here, you said A between -1 and 1.
Oh, yeah. I am not sure because I tried the function in PyTorch. They follow the equation over here. It works from 0 to 2. So I think it doesn't matter the range. But anyway, just a range. If they only limit it in -1 to 1, we can just map them back. This is not a big deal, I think. But my point is I cannot tell what happens if they just transfer it to between the 2 to 0 to 2. I cannot tell the difference between them. So
yeah, I got another question. So what if your A takes to be 1, then phi will be half pi, right?
yeah.
A equals to 2, then phi will be pi, and then tangent of phi over 2 will be tangent half pi, right? It will be infinity.
Yep. Yep. So they have the I think they have the chirp function over here, not chirp function, the impulse function over here. I mean, here is approximation ways, and here is some special case we have to prevent, like the case you said, if it's just a 90-degree angle, how do we prevent it? They said if alpha plus pi is multiple of 2 pi, then yeah, they use the
Oh, so
impulse
just mean
function here.
yeah, from the rightmost block is just a way to approximate the fractional Fourier transform definition in one, right? So so you provide, so the equation 1, 2, 14, 15, 16 are just a way to compute equation 1. Am I right?
Can you repeat the question again? I didn't get it.
Equation one is the definition of the fraction Fourier transform, right?
Yep.
And then to compute this Fourier transform, this fractional Fourier transform, you can use the step 1, 2, 14, 15, 16, as you just talked about, right?
Mm-hmm.
That's the way to compute one.
Yep. Yes.
So alpha will be, the alpha in one will be A defined in 14, 15, 16, 1 and 2, right?
Mm-hmm. True.
Yeah, but in the original definition, the fractional Fourier transform alpha you don't have a restriction on alpha values. Alpha just if alpha is not multiple of pi or 2 pi and so on, you can also you always have a valid definition, right?
Yeah. Yeah, just we don't handle the special case from it.
Okay.
Mm-hmm.
Yeah, I kind of like feel suspicious about the A and the alpha, because in the definition in the middle, you said if alpha is a multiple of 2 pi, right? It will become a impulse function. And but if A equals to 2 pi on the right block, phi will be, I mean, time h of phi over 2 shouldn't be problematic, right? It seems that you can also compute this.
Yeah, I probably confuse you guys. So the alpha here is the degree, which means is the degree in pi, and the alpha here is just a real number, but to transfer the real number to how much pi, I mean the alpha here is just the phi over here, so I probably just confused you guys. Yeah.
Alpha in the middle corresponds to phi in the right. Is that what you're saying?
Alpha corresponds what?
Alpha in the middle is actually the phi on the right.
Mm-hmm.
I think that makes
Yeah.
sense.
Yeah,
Because
true.
when phi becomes a multiple of 2 pi, you divide by 2 will be, there's still some problem, like 2 phi phi over 2. If phi is pi, multiple of phi, okay, if a phi is multiple of pi, then tan h of half phi won't be meaningful, right?
You mean
Yeah,
You
if
mean
phi,
which one?
yeah, for example, phi on the right, if it is pi, then what is the tangent of half pi? It's infinity.
Yeah.
But it looks like your definition in the middle doesn't have any restriction on that, right? If alpha is pi.
Oh, you mean approximation
Yeah.
here?
Yeah.
Probably they have, but I didn't post on here.
And in the middle, you said if alpha is not multiple of pi, then what is if the alpha is multiple of pi?
Like,
Oh, you said if alpha is alpha plus pi is a multiple of 2 pi, right?
yeah,
Right.
it means when the alpha equal to 2 pi, 4 pi, 6 pi, like that,
And if
is
alpha
the
equals to pi, 3 pi, and 5 pi, it will be the second case, right?
third this
the
one,
third
yeah.
case. The third
Yeah.
case. Oh, okay. Then that explains. Then I believe alpha corresponds to phi on the right. Because it covers the case. Right? When phi equals to pi, 3 pi, or 5 pi, or pi equals to 2, I don't know, 2 pi. What is tanh of 2 pi?
Where?
I mean, what is tangent function of pi? So sine pi or cosine pi. It should still be valid, right? But sine pi will be sine
Oh,
phi.
yeah.
Yeah, sine phi will be 0, like a phi will be infinity. Okay, yeah, I just want to find the correspondence between the way to compute fraction Fourier transform as you talk about on the right and the definition. So they are exactly the same, right?
Yeah, they are the same, but just some simple definition, probably a little bit different from each other. But yeah, they are the same.
Okay.
Yeah. So in the FNO, they impose the kernel function as list one, which can turns into the convolutions form. And I'm thinking if they are right, I mean they are right, but the convolution form is not as simple as the Fourier transform form, which means we probably it will be too simple just transform this one to Fourier domain and transfer this one to Fourier domain and multiply them together. It will be too simple. Probably there is a more generalized form. And there's another paper they discuss about this problem, and they present a theory, say, yeah, there's a generalized form. So in the case when the alpha equal to half pi, this one just equal to the regular Fourier transform. And by different case, it can transform the data to alpha domain. I mean, the F over here is the data we observe. The G over here is the kernel function we want to solve. And in this theorem, by transform them to alpha domain and multiply them together and multiply with the transfer function again, they can get the result in alpha domain and the rest of the things we need to do is just transform them back to the time domain.
So it still needs to assume your kernel is a stationary, right? Is a translation invariant.
Well, what do you mean?
I
Station.
mean, the convolution theorem tells us if you convolve some kernel k must be the function of x, the difference between the two inputs. That's called translation invariance. Then you can apply the convolution theorem. So here is the same requirement, right? You have to assume your k has similar form, like it is only determined by the difference between the inputs and the xy, right?
Okay. I didn't check that to detail, so I probably have to check that.
Yeah, you
Probably,
need to check that.
yeah.
I guess they're gonna use the same constraint. That means you have to assume your convolution, your kernel must be translation invariant.
I have a
Okay.
question. So what is the complexity of the FRFT?
So it
FFT
depends.
can be FFT can be a log n, right?
Yeah.
Is
So
there any fast computation of the FRFT or inverse FRFT?
I think it's just, so the way we need to do is to multiply here and do the convolution over here and multiply again. So it probably have to do 3 steps, which calls us the n plus 3 n log n and plus n again, I think. The n over here is the first multiplication, and the 3 n log n is
So
the
basically you're saying calculating
convolution here.
can also leverage the fast Fourier transform, right?
Okay, I see.
It's much slower than the FFT, but it's way faster than Wavelet. So I think it's a promising way to calculate the result.
No, in terms of time complexity, they're the same. It's just a additional
They're the same, yeah.
additional a little
It
bit.
doesn't matter. Yeah.
Okay. So next I'm going to talk about what did people do during recent 20, 30 years. So in this paper, people just mention by sorry guys, it's 1:15. I have to
Now to
check
leave.
the exam. Yeah, I'm sorry.
Okay, that's fine. That's fine. That's good to it's a very good introduction to this fractional Fourier transform. We can discuss about it offline later.
Okay. Thank you.
Okay. Yeah, hope you are doing good in your exam. Yeah. Okay, Xin, please continue. Where is he? I cannot hear you. You're muted. No. Yeah, you can unmute. I saw you're muted.
Okay.
Yeah.
Okay. Yeah, ever continue the post-training quantization with the last topic of the rounding. So yeah, as we introduced before, so we will do maybe we can look at the formula about. Yeah, so when we look at the quantization formula, as actually for this one, that's the recover from the integer to the float. And when we do the quantization, we need to do the mapping from the float to the integer. So we firstly we decided the we decided the scale factor and also the 0 point, and then we can calculate the Q. And actually, when we do this, we need to divide R by S, and then do the rounding, and after the rounding, and then add Z. So the rounding step here is rounding R divide S. And for the rounding itself, in general, it would be rounded to the nearest. So somehow, if the R divide S is equal to somehow like the 1.2, then it will divide to 1. And actually here there are some variance of the algorithm. So when it, for example, in this vector, it has a value from 0.3 to 0.7, and if it rounded to nearest, assume we only have 1 bit to represent them. So the one close to which close to the maximum would be 1, and the values which are close to the minimum value 0.2 would be 0. This is a rounding to the nearest, and in this paper, that's the adaptive rounding for weight quantization. it proposed one method named add round. So somehow for the value 0.5, it is rounded to 0. So what the motivation in this paper is that although rounding to the nearest for each single weight can be optimum for that weight, but for the overall net model performance, rounding to the nearest may be not the optimum. And yeah, I can. And actually, in their paper, they shows they have one example for that. We can take a look at of the paper. So this is one example. So firstly, the motivation is that it tries to estimate the error after the quantization. So with the W is the original weight, and the delta W is the error between the quantized weight and the original weight. So with this formula, it's possible to estimate the change on the loss by the Taylor expansion. So for the Taylor expansion, the most important terms are the first order gradient and the second order gradient term. That's the Hessian, and with in this example, it focuses on the second order term. For the second order term, assume this Hessian matrix have some simple is a simple 2x2 matrix, and when we calculate the second order term, actually it's equal to the summation of delta W1 square, delta W2 square, and multiply delta 1 and delta W2. So if we only look at the error for each single weight, actually that's the diagonal of this matrix, but actually it has one additional term that's the dependency of the delta W1 and the delta W2. So in this case, if delta W1 and delta W2 have the same sign, for example, both of them are positive or both of them are negative, then the error from this term would be large. And if they have different sign, and this would decrease the error caused by the quantization. So in this paper, the adaptive rounding method, it by optimizing the error estimated from the Taylor expansion. It tries to count the dependency between the weights and to improve the overall quantized model performance. Yeah. So this so for here, this is the basic method. For this one, actually, that's the rounding to the nearest, and then and for this method, it rounds to the floor rounding of the value, or to the cell rounding of this value. So it can alternatively represented by the flow rounding at one sigma. So for sigma would be either 1 or 0. So for this method, actually it will not rounded to the nearest number. It have two options. And it used some method to achieve that. So firstly, it introduced some additional random variable of the same shape as the weight, and then it also introduced one regularization term, the FV. So for FV, it will try to force the HV to be close to 0 or 1, and the HV here is try to learn the delta here.
So V is consist of delta. What's the definition of V?
V is the additional variable introduced to learn delta.
And what's the relationship between V and delta?
Delta is equal to HV. The function HV is equal to delta. Yeah.
Okay. So yeah, okay. So I just want to treat V as a free variable. Okay.
Yes. So it will learn it will feed forward, run the feed forward of the network with a few data, and then it will learn the function HV and decide the delta, and then fix the delta for quantization.
So here your data is just a set of X. Just to prepare a set of text, and then see if you can. I don't know.
Yeah, for that I need to check the paper. So I forgot that they use the real data, or just use some random.
Okay. Then this applies to every tensor, right?
Yes, every weight.
Tensor-wise, it's a tensor-wise approach. Like when you have a different weight tensor, you have different V.
I think this for every element in one tensor. So if the matrix is 3 by 3, and then the HV would be 3 by 3.
That's too large, right?
But it doesn't matter. It just need to learn it, and then quantize the model. We only need the quantized model, right? So it doesn't matter.
You have to prepare the same size of the model, the parameters, additional parameters of the same size of the original model.
Yeah. So I think for this paper, the most valuable thing is that, in general, we think the rounding to the nearest is optimal. But this paper provide a little another perspective that we maybe can round down or round up, and
yeah. It's a neat idea. I mean, but in terms of optimization they have done, I kind of hard to believe that they set V to be exactly the same as W. Your W can be huge, right? How do you minimize a huge V? Or like W could be 4096 times 4096 times 128, right? You have to learn a V of the same size.
Yeah, I see your concern. So if one V is large, maybe it's not easy to learn. I guess maybe that's why the regularization term are used here. It will force it to be 0 or 1.
It's a soft regularization. You're still doing, and the second thing is how do they back propagate to the gradient? You're doing the rounding, right? It's a step function. How do you?
So for the h itself, it's a continuous function. So it's somehow like use the sigmoid function for.
Yeah, but you first do the floor rounding for W. You plus your HV, then you do the.
Yeah.
You do the ceiling. No, you do the floor again, right? I think you're yeah. This should be floor, right?
Yeah.
So it's like ReLU. It's similar to ReLU, right? Maybe they can still do some subgradient on there. Yeah.
No. So I think this is the rounding, not a flow for the outside, because HV, the output in the range 0 and 1, it can be close to 0 or it can be close to 1. So it's still a rounding. Yeah, but you are right. So back propagation would be not continuous.
Yeah, then you have some if else statement, right? You can calculate some subgradient, I guess. It's like when you backpropagate through ReLU, it's similar to that, but it's a little bit more complicated.
Yeah, I guess so.
Yeah.
It makes sense. Yeah. Yeah, so I just want to introduce this idea here, and I didn't put the result of this paper in the slide, and maybe we can check some result. Yeah, so it seems for some rounding to the nearest, the performance are very low, and the rounding can improve them a lot.
This is a perplexity.
No, this is on ImageNet, on ResNet 18. So for the yeah, actually the initially the quantization are applied on the regular model.
Okay.
Not it's because in recent year the large language model became popular, so people are only working on large language model now.
Okay.
Yeah, but I don't know. Yeah, this result is very impressive. I'm not sure why the rounding can improve so lot. Yeah, but today I only want to introduce this concept that the rounding to the nearest maybe not the optimal. So I think that's it. So for today, I introduced the linear linear quantization. For the linear quantization, there are a few things we can. Firstly, the 0 point, the asymmetric or the symmetric, and the scaling granularity. So in general, the beta granularity, it will take the beta performance, but it also will take more storage, and to save that, it's possible to use the multi-level group quantization, and also it's possible to do the clipping on the maximum value of the range, but the range clipping are mainly used on the activation quantization, and the last one is the rounding. So it somehow shows that the adaptive rounding can perform better than the round to nearest. But as I know, the round to the nearest are still the most the mainstream in quantization, because it's more it's pretty simple. I think that's it today.
Okay, great. Yeah, that's very good. Great introduction about quantization work.
I forgot to mention that actually most slides for today are borrowed from one course called the Efficient Deep Learning, lectured by Han Song at MIT.
Okay. Okay, any question to Xin? Yeah, if there's no question, I think we can stop here today. And thanks, Xin, again. And hope everyone has a great Thanksgiving holiday. Xin, you just hold on. I want to talk to you for a few minutes.
Oh, okay.
Okay. Yeah, I will see you.
Okay.